Okay, so ladies and gentlemen, we are going to have a conversation around spanning tree protocol, which is called STP. In the previous CCNA version, STP was a very famous topic, but the portion of it, especially dealing with the configurations, they took it to CCNP. Okay, but I'm going to try as much as possible just to be able to give you as much information as possible when it comes to CCNP. So let's start by talking about, what exactly are we going to cover this evening. So we'll explain the common problems within redundant layer 2 switch networks, and that will tell us the major purpose of STP. We look at how does it operate, and then how it has been evolving ever since. Okay, and so to start my class today, I actually want to go straight to illustrations. I like using illustrations a lot so that we can be able to see what happens when a network does not have STP, or why do we need STP in our network. So I want you guys to check on just a bit keenly on this and see what's going to happen. So first and foremost, I want you to note that we do have 3 switches in this network: switch S1, switch S2, and switch S3, right? We all know that a switch has a special type of table called a MAC address table, all right? And the MAC address table, we have been learning so many times that it's a very important part of the switch, because the switch relies on it to do just so many things, Now, we do know that every time a PC connected to a switch sends a message to the switch is going to record 2 things. Number one, the switch must record this, the source MAC address of that PC. Let's say PC1 is sending something to switch S2. In the MAC address table of S2 must be recorded the MAC address of PC1 together with the port number, which is F011 in this case, okay, of PC1. So the source MAC address and the source port number. It doesn't matter where this PC is sending the message, whether it is going to PC4 or it's going to PC3. It's going to record the source MAC address and the source port number, okay? Now, sometimes the switch can get confused, and right now I want to explain what happens when we don't have spanning tree enabled on a switch. Of course, every switch has spanning tree enabled by default, all right? Now, if we can be able to talk about the effect of the absence of STP operation in a switch, then that is how you are going to learn that the STP is very important in a switch. So let's see the consequences, and I always tell people normally that if we as humans could know the consequences of some of our actions, trust me, we will always stop those actions before we take them, because we already know the consequences. But that is the approach I want to use here today. We want to look at the consequences of the action and then now study the importance of the functions. If you have a small child playing with the razor blade, and it might not be sufficient enough to tell the child to stop playing with the razor blade. But if you allow the razor blade to cut the hand or the finger of this small child, they will actually know that a razor blade can make the finger to be painful. And worse of it can make the fingers to ooze blood, and that is not a very good sign. And so the child will never play with the razor blade again. So let's look at, ladies and gentlemen, the effects of the absence of spanning tree in a switch. All right. So let me activate this a simulation here and look at what happens here. Remember what the switch does? When a switch receives a a broadcast frame from a PC. The switch is going to broadcast it to all the active ports. Active ports means the port is connected to something, a device, either to a switch or to another PC. So in this case, this switch is going to broadcast the message to S3, to S1, to PC3, to PC2, except to PC1, F011. Why? Because a frame can never come back to where it came from. And that is something very, very important. So let's see what happens here. And I want you to be a bit keen here. So look at that. Switch S2 is going to broadcast the frame out of all the ports except where it was received on F011. And you can see that is something that has already happened. All right. The next thing that we're going to be seeing here, look at this switch. This is switch S3, I suppose so. Yeah. Okay. Okay. Now, what is switch S3 going to do? Switch S3 has received a frame from S2. Okay. So switch S3 is going to forward it to S1, and switch S3 can never bring it back to S2 because it has been received from S2, from F02. See, fast Ethernet 0/2 is where this packet is being originated from. And for S1, it has received the frame on F01. So it can never send it back. So switch S1 is going to forward it to PC4 through F03. And switch S1 is going to forward it to F02, going to S3. And so at that moment, I want you to note something. I know it hasn't happened, but it's going to happen. The same frame originated from PC1 is being broadcasted to S3 and to S1 from S2. But what does S3 and S1 do? They're going to exchange back the same frame. And if the frame has been received from S3, is going to receive from S1 the same frame, and S1 is going to receive the same frame from S3. And so if S1 receives the frame from S3, it means that frame has come through F02 and it can never go back to F02, but S1 can send it to PC4 and S1 can still send it back to S2. Ladies and gentlemen, that's a problem already there. If you have not seen that, let me explain from S3's perspective. S3 will receive, S3 will receive a frame from S1, and S3 cannot send it back to S1, but S3 will bring it back to S2. And note what happens. The same frame that left S2 to go to S1 and to go to S3 is going to come back to S2. The one sent to S3 from S2 will come back through S1, and the one sent to S1 will come back through S3, and they will converge back here again. And because S2 has received each of these frame from those different directions, S2 can forward the same frame back to these other devices. And that is a terrible mistake, And remember, one of the objectives of the switch is that a switch should never receive a frame it had sent, especially through the port it had sent them from. And let's keep on looking at this. Look at what happens there. Look at what S2 and S3 and S1 does. Look at them. Look at them there, guys. All right. All right. Almost. They are receiving the same frame. They are exchanging the frame. And when they exchange the frame, they're going to bring it back to S2. And that is one of our most terrible mistake. One of the most terrible mistake. This one here, this one should never happen with a network. That switch S2 should never receive something it had sent to switch S1 and S3. All right? And that is, and look at that. Look at that. Whatever came from S3 goes back to S1. Whatever came from S1 goes back to S3 and is broadcasted even to the PC that had sent it. PC1 is still receiving the same frame. Now, one of the things that affects is this. Look at this. I want you to note this. S2 initially recorded to have received the frame through port F011, a frame with the same source MAC address. All right. Now, when the same frame is being received back to S2 from one of the switches, switch S1 and S3, it is going to record the same MAC address with a different port number. That is terrible. The same MAC address of that frame, same frame, but switch S2 is going to be confused. It's going to ask, can I record it at F011 or F02 or F01? Because you're receiving the same frame, but with different port numbers. And that is so confusing. Now, not only that, let's look at it now. If more than one PC, and by the way, we are assuming this network is lacking spanning to protocol. It has been disabled. And that is a mistake you should never do for your network. Let's look at something that we call a broadcast storm. What we have seen first there is called a layer 2 loop. A layer 2 loop is when a frame is received back to the device that had sent it. So look at this triangle here. The frame left S2, went to S3, it went to S1, came back to S2. One left S2, went to S1, came to S3, came back to S2. And you can see the loop, that circulation, and it can still go back and go back and go back. And I want to see that going back and forth. And we're gonna give it a name and we call it a broadcast storm. We're gonna call it a broadcast storm. And so let's see a broadcast storm in action. Let's look at a broadcast storm in action. And so in this case, PC1, which is where the frame is being originated here, is gonna send a frame to S2. Obviously, and now it's going to be a bit faster. We are going to see a multiple version of what we have seen first. Switch S2, of course, is gonna broadcast it to S3 and to S1, okay? S1 will bring it back to S3, S3 will take it to S1, and the frame will come back to S2. And it will keep on going. And then this time around, we'll have PC2 produce its own frame and to start going round and round to cause the layer 2 loop. PC3, PC4. Actually, it will go one PC at a time until one of the PCs will produce the last frame, which will find the network so busy doing several layer 2 loops within the network, and the network is going to come to a standstill. And that is what we are going to call a broadcast storm, because we're going to have so many broadcasts on the network. So let's look at this, guys. Let's look at this. That is the first packet there in yellow. Good. And the broadcast is moving. The layer 2 loops, sorry. And the second one, you can see, is orange. Okay. And orange is beginning to form the layer 2 loops there. And the third packet is now green. Green is beginning to broadcast. Look at this. And then the fourth packet, which is now purple in color, comes to the network, and the network is so busy. You know, there's so much broadcast going on in the network, and the purple packet cannot move. Guys, I want you to mirror this in a real-time network. Now, in a network, a production network environment, in an organization or a company, you realize at some point when all the employees are complaining that the network is very slow. Why? Because they're trying to access the company resources. It might be a server or something like that. And the browsers are all just loading. All the browsers are rotating. They're just loading and loading and loading continuously without stopping. And that is not a very good thing. Okay? That is not very good. And that should be something that should worry you. And so this is one of the things that can cause the going round and round of, I mean, the continuous loading of your browser without yielding any results, I can do it again, you know, for the benefit of doubt, so that you can see that. So look at the first packet in yellow, and the layer 2 loops is picked up very well. The second one is orange, produced by PC4, and it gets to S1, and the layer 2 loops begin, and you can see the layer 2 loops there. The third one is green here, and the green gets to S2, and S2, and it begins to do the layer 2 loops there. And by the time PC2 is producing the purple packet, it finds when the network is busy, we have too much layer 2 loops, and the network becomes unusable, you know. And that's the point when you, the network administrator, start receiving so many calls, you know, Mr. Network Admin, we can't access the resources. And that's when, you know, you can even be fired as a network administrator, because you have brought the company business at a standstill. And when the company business is at standstill, it means that the company begins to make losses at that particular point in time. All right. Now, let's look at in a situation where we have spanning tree protocol. So this is a very good situation now with spanning tree protocol enabled. And so at a glance, what spanning tree protocol does is that spanning tree protocol will always block one of the ports here. All right. Spanning tree protocol will block one of the ports, so that there's no way a message could leave S2 and come back to S2 in either directions. That's not going to happen. And so look at this. So, and the blocking, by the way, is not done with the command no shutdown, or the command shutdown for that matter. The blocking is done internally using the STP protocol, which is called the STA, the spanning tree algorithm. All right. So it's blocked in software. And I'm going to tell you what happens, you know, I'll tell you what happens the other way around. So look at that frame. It's broadcasted to PC2 and PC3 and S1. S1 broadcasts to PC4 and S3. All right. S3 tries to send it back to S2. It can't get in. That port is blocked by spanning tree protocol. That is the work of spanning tree protocol, to prevent those broadcast, I mean, the broadcast storms and the layer 2 loops, especially the layer 2 loops. Now, what if someone turns off using the command we have learned, shutdown? What if someone shuts down F01 or F01 of S1 or the one on S2, so that this link here is blocked? What is spanning tree going to do? You can see that here. So someone decides to either destroy this F01 or unplug it from S1, or just to shut down this port using the command shutdown. So what's going to happen here? Let's see that. So when that happens, spanning tree is going to realize that this port has been blocked, and so spanning tree is going to open the one that it had blocked itself. So it's going to be something like this. Okay. See that? So PC1 sends a frame, and the spanning tree realizes that this port is manually blocked. So it opens this one, and the frame can now go through S3. From S3, of course, to PC2 and PC3. S3 sends it to S1, but S1 can never bring it back to S2. And that is the objective of spanning tree. That is the major objective of spanning tree. The frame should never come back to where it was originated, or from where it was originated. All right. Let's see, keep on learning here. And let's look at this diagram here. All right. This diagram, For this one, I think I'm gonna need responses from you guys. I'm gonna need response from you guys. There's Nelson is here, Florence is here, Leonida is here, Lavins, and then we have Fred. So for this one, please everyone be keen because I'm going to need an answer from each of you. You can see we have how many switches over here? We have 8 switches from switch S1 up to S8. Now, because you guys, without any doubt, attended primary school, class 3, 4, 5, 6, up to 7. All right. And we studied mathematical shapes. You know, we studied triangles, we studied rectangles, we studied trapezia, we studied parallelogram. Basically, we studied 4-sided figures, 3-sided figures. Rhombus was there. You know, parallelogram, there was a trapezia, there's rectangle, triangle, and all that. Now, what I want you to tell me is how many complete shapes do you see here? It doesn't matter even if they repeat. And I'm going to start with Nelson. Complete shapes, you know, something that you can, that can form a loop, like S1, S3, S5. So how many complete shapes or how many complete loops can you see from this diagram? Let me start with Nelson. Nelson, how many complete loops can you see here?
I see 6.
Nelson sees 6. Thank you. Thank you. All right. That's great to hear. Let's go to the next person is just a minute. The next person is Florence. How many complete circles? Complete loops, sorry. How many? Do you see? Do you have Flo here? Oh, Flo wants to answer later on. It's okay. Leonida, tell us, it's your turn. How many complete loops?
I can see 5 of 5.
Thank you. Thank you. Good, good, good. That's a good one. Lavins, tell us how many complete loops can you see?
I can see 3.
Can see 3. Very good. Very good. All right. Fred, how many complete?
I can see they are around 6.
6. Very good. Very good, guys. So we have 3, we have 6, and we have 5. And Florence has not talked. I don't know why she didn't talk. Florence, can you tell us something, please? We don't want to leave you behind.
I can see 5.
5. Thank you very much. Thank you very much. All right. All right. All right, guys. We're going to count it together. We're going to count it together and we see how many are they in total. All right. So let's start by counting this triangle S1, S3, S5. This triangle number 1. All right. Okay. Number 2, we count another triangle here. S4, 5, 8. Second triangle, 4, 5, 8. Correct. Another triangle, of course, is the bigger one, the bigger triangle. 2, 3, 8. That is 3 triangles so far we have counted. All right, all right. That is 3. Then let's go to the fourth one. The fourth one, we take this looks like a rhombus or a parallelogram. It's not drawn to scale. 2, okay, 1, 2, 4, 5. That is number 4. All right, 1, 2, 4, 5. Good. Then we go to a trapezium, the first one. 2, 3, 5, 4. That is number 5. That is 5. That is 5. And then we did 5. I don't know whether we are done. I don't know whether we are done. Let me start again. Let me start again.
There's
Okay.
another one.
There's another one. Okay, let's start afresh. Let's start afresh. 1, 3, 5. Number 1. Count with me. 1, 3, 5 is number 1. Okay. 4, 5, 8. Number 2. Okay. Then that is number 2. Then we go to 1, 5, 4, 2. 1, 5, 4, 2. That is the third one. Okay. Then we go to 4, 5, 3, 2. 4, 5, 3, 2. That is number what? Number 4. Is that number 4?
Yes.
Okay. All right. All right. All right. Once you do that, number 4, then you do 1, 5, 8, 4, 2. This is number 5. This is number 5. Then the 6th one is now the big one. Are we? I think we should be together on that. Or someone has another one. Okay. 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 Thank you very much. So we can see 6. 6. I mean, if we were in class, we will be clapping, you know, for those who said 6, and those who said 5 were not very far from it as well. But you know, please just feel good wherever you are. If you said 6, just shake your head and say, I made it. You know. Anyway, so we have 6 loops over there. We have 6 loops over there. Now the thing is this, guys. The thing is spanning tree, because this can be, you know, a network. Spanning tree, I'm going to show you what spanning tree is going to do. Spanning tree is going to make sure that it's going to block some of the ports. It's going to block some of the ports such that you can never go through a complete figure here or loop without meeting a blocked port. Let's look at that. And you can see that here. If we take the first small triangle here, this port is blocked. If you go through the big triangle, 2 ports are blocked. If you go through triangle 4, 5, 8, 2 ports blocked. If you go through triangle, or trapezium, 2, 3, 5, 4, there's 2 ports blocked here. If you go through trapezium 2, 8, 5, 1, there's a port blocked here. All right. If you go through triangle 2, 4, 5, 1. So at every point in time, we can never have a complete loop. That is the work of spanning tree. Okay. Because those loops, they are very dangerous to a network. They are the ones that will cause the broadcast storms. They're the ones that are going to cause the broadcast storms. But as we are going to be learning, the blocking does not happen mechanically. All right. What the switches have to do is that the switches have to elect one among themselves, and they do a logical election. And the one that will be elected will be called a root bridge. And you can see our root bridge here is S1. And normally, you know that switches, normally, we learned how to create VLANs the other day. You know that every switch is only born or is only manufactured with one default VLAN, which is VLAN 1. And so this is what we call, this is a one VLAN instance, because all the switches are currently having only one VLAN. And so they will only do an election for one switch to become a root bridge. Okay. Once one of the switches has been elected as the root bridge, then to make sure that, you know, blocking is going to take place, each and every port of every switch, listen to that, each and every port of every switch is going to be assigned a specific role. You get that? Each and every port of every switch is going to be assigned a role. And the role is going to be either of the following. Either it will be a root port, okay, or the port will be a designated port, or the port will be an alternate port. So root port, designated, alternate. Now the root ports, all ports that are root ports and all ports that are designated, all of them will forward traffic. Now, the port, any port that is be given the alternate role are the ones that are going to be blocked to prevent the formation of the layer 2 loops. Listen to this. Any port connected to an end device like a PC or a switch, a PC or a laptop, all those ports are going to be designated ports. Those are important ports to note. So any port that is connected to an end device must be a designated port. And any ports on the root bridge must be a designated port. I'm going to repeat that, guys. I know it can be confusing, but that's why I'm here. That's why I'm here. It can be very confusing, but that's why I'm here. Now, I want us now to, there's a video here you guys are going to be watching on 518. Please do observe this video here, 518. It contains everything that I have talked about, everything that I have talked about. And so I want to take you back to my PowerPoint slides to continue getting more info about spanning tree, So I might be skipping some of the PowerPoints because these ones are the ones we were demonstrating for the simulation. So the PowerPoint does not have these packets moving, but we did see it on the wall, and you can see, the calculation process and all that. Remember, I also did mention that the STP means spanning tree algorithm, and algorithm, the name of the exact algorithm that makes spanning tree to work is called STA, spanning tree algorithm. And it is the major role of STP is to prevent the layer 2 loops from occurring by configuring paths that are loop-free, paths that cannot form loops through the network, and strategically or logically placing some ports on blocked states to prevent the formation of the layer 2 loops. The blocking is always done dynamically or automatically, and they can be unblocked depending on how the topology changes, Let's get into the nitty-gritties of STP. We have already seen how it happens, what happens, but now what are the facts? What are the details? Because we are told that the devil is always in the details. The real things are always in the details. So like I said, when a switch is powered on, all our switches, by the way, all switches have some element of spanning tree running, because if that is never there, then that's when we come up with those broadcast storms. And that means, please never say no spanning tree. You should never say that in your switch. You know what's gonna do? It's gonna disable STP. So the first thing is, when a switch is powered on, it needs to do the first thing. It needs to elect which switch is gonna be the root bridge. I'm gonna tell you how the election takes place to elect the root bridge. Once the root bridge is elected, then the switch start now doing election on the ports. Elect the root ports, which ports are going to become the root ports, which ports are going to be the designated ports, and which ports are going to be the alternate ports, which are also the ports that are going to be blocked. All right. Now, in the election process, between the switches, whether the switches are 2 or they are 1,000, the switches exchange among themselves messages we call BPDUs, Bridge Protocol Data Units. All right. So these are the messages, the Bridge Protocol Data Units, the BPDUs. They're used to share informations among the switches. Okay. And they elect the root bridge, they elect the root port, they elect the designated ports, and they even elect the alternate ports. All right. And each BPDU message contains what is called a bridge ID. And basically, each bridge ID is just an identification of each switch. Okay. And decisions, major decisions that are made must always be done using this, using the algorithm, and the algorithm uses these messages here. So the bridge ID contains 1, a priority value, which I will tell you more about it. 2, it can be the MAC address of the switch. And finally, what is called an extended system ID, an extended system IDs. And the lower either of these values, the lower the bridge ID is always the better. In fact, the switch, any switch with the lowest ID will become the root bridge. Talking about the bridge priority, the priority value, by default, all Cisco switches have a default value of 32,768. All right. By default, all switches have a default priority of 32,768. But this number, you can actually configure it. That means you can change it. But there's a rule of changing it. You can only change it from 0, and you keep on adding 4,069, 4,096, 4,096. So the priority value can only be assigned in the increments of 4,096. So from the first one is 0, the second one is 496. Okay. The next one will be 8,192 as you increase with 4,096. Now, listen to this. The lower the value, the better, because the lowest priority is always the one that is preferred. And that means if you ever have a switch with a priority of 0, it will always take precedence over all the other priorities. All right. So that is a priority. And priority, number 1. Okay. So the priority will always be used as the first election point for electing the root bridge. Let's say all the switches have the same priority of 32,768. 32,768. If all switches are only having the default priority, you, the network admin, or no any other network admin has changed it, we go to the next thing for the election called the extended system ID. Now, the extended system ID is always the priority plus the VLAN your switch is having. All right. Guess which is the VLAN that all switches have by default, VLAN 1. So the extended system ID of your switch normally will always be 32,769, which means you take the default priority plus the default VLAN, which is 1. So 32,768 plus 1 will be 32,768, 32,769. You just add the VLAN 1. If a switch is having VLAN 20 or VLAN 2, all right, you just add the 2 on top of the default priority to get the extended system ID. And that brings me to something which I will tell you later on, that if a switch has several VLANs created, then every VLAN will be having its own spanning tree instance, which means every VLAN will be electing its own root bridge. And so every VLAN will be having its own blocked ports and designated ports and root ports because of what is called a VLAN spanning tree protocol. I will tell you more about that. So each VLAN is going to have its own ports states. Okay. Now, let's get this clearly here. If the extended system IDs are all the same, all right, our extended system IDs are all the same, then the last breaking of tie is going to be done by the MAC address, which you know can never be the same for those devices, all right? Unless in very special circumstances. And so since each device has a unique MAC address, the MAC address is always the last option to elect the root bridge. So the switch with the lowest MAC address will become the root bridge. And that is something very important. So these three, very important. Now, as we had already mentioned, the first thing that happens is always the election of the root bridge, the election of the root bridge. And so I want us to look here very keenly and observe how the root bridge is going to be elected here. So we have S1, S2, and S3, all right? And each switch has a priority value. S1 has 24,577, S2 has 32,769, and S3 has 32,769. Obviously, S3 and S2 have the same priority, but S1 has the lowest priority. And that's why S1 is going to become the root bridge. Ladies and gentlemen, this is a very common question in the industrial exam. I've never seen them bring complex questions for spanning tree protocol. It's always election of the root bridge by either using the priority value, but they love so much, they love MAC addresses. They love the MAC addresses. So in this case, you can see the election of the root bridge has already taken place, and we have seen that S1 is going to become the root bridge. Now, what if all the switches had the same priority of 32,769? Okay, I hope you understand where 32,769 comes from. It's 32,768 plus VLAN 1 contained in each switch. Now, if all switches had the same priority, then we'll go for the MAC addresses here. And you can see this MAC address here. We can see that, that the MAC addresses here are actually different. And this, here we have 00A, 00222, 00A, 00333, and here is 00A, 001111. Obviously, switch S2 could have become the root bridge because it has the lowest MAC address by the 111 that is there. All right. Moving forward, we have seen that this election of the root bridge has already taken place. And now we need to go to the next thing. Okay. So the next thing is now something I've already talked about. Of course, how we get 32769 from 32768. I already talked about that. I've also explained to you what happens if in case of default bridge IDs, what's going to happen. I think I already talked about that because S2 it has the lowest MAC address. That is something I have already talked about. Now I need to talk about now something called the root path cost. Okay. So when the root bridge normally has been elected, okay, and now the switches need now to start doing the election for the root path. Okay, we do have what is called the path information, which is basically the internal root path cost, which is normally determined by the sum of all the individual path costs along the path from the switch to the root bridge. And I want to save you guys from, having to struggle so much, but make sure you get these details here. So when talking about STP, because this is the default spanning tree version, We'll of course go to RSTP later on. So for the default STP, you know that we can have different port speeds or link speeds. We can have a link speed of 10 Mbps, 100 Mbps, 1 Gbps, and 10 Gbps. So there's an inversely proportional value. Values between the speeds here and spanning tree path costs. So what you're going to note is that the lower the speed, the higher the path cost, and the higher the speed, the lower the path cost. And so a link speed of 10 Mbps has a cost of 100, and a link speed of 100 Mbps. And please remember one thing here: any port that is F something, fast Ethernet 0/1, F0/2, F0/3, those ones are fast Ethernet ports, and their speeds in most cases is always 100 Mbps. And that means their cost is always 19. Why am I emphasizing that? Because you're going to need that knowledge in a few minutes. So fast Ethernet ports have speeds of 100 Mbps, and they have a cost of 19. Gigabit, when you see G0 something, G02, G03, okay? These ones are gigabit Ethernet ports. They have a speed of 1000 Mbps. Their cost is 4. Very important. These are the two most common ones: cost of 19 and cost of 4. Of course, ports of or link speeds of 10 Gbps have a cost, STP cost of 2. These are just costs. They don't have units, please. Of course, we have the equivalences of RSTP, the Rapid Spanning Tree Protocol, which is now from 2,000 to 20,000 to 200,000, all the way to 2 million, But, our focus currently is the default spanning tree, and that's what we're gonna be looking at right now. Now, that was a by the way. Let's look at, after electing the root bridge, the next election is now for the root ports. It's now for the root ports. And since this next election is for the root port, okay, we are basically going to see how do we elect our root ports. And so the first thing to note is this: if S1 is our root bridge, all right, all the ports on the other end of the other switches connecting to the root bridge. So this port here, okay, and the ports here, these two ports must always be root ports, okay? And why am I saying that? I'm saying that because if one end of the port is always designated, or root port in this case, the other end must always be designated port. So these two ends of the switches joining to the root bridge, these two ends must be root ports. Very, very important, okay? And once more, we can do that by looking at something here. Look at all these ports are actually fast Ethernet, like F01, F01. So this is a fast Ethernet link, which means the speed is 19, okay? This is here, another fast Ethernet link here, F02 to F02. The link here, the speed is 100 Mbps, and that means the cost is 19, okay? Then, again, F01 to F02, this link here, all the ports are fast Ethernet, and the cost is 90. So we have 19, 19, 19, okay? Now, you realize that when we were looking at the MAC addresses of these our three switches, of course, S2 was the root bridge, and we had used the priority. But when you compared S3 and S2, S2 actually had a lower MAC address, even though they had the same priority. And so S2 in spanning tree has some superiority to S3. And so we can be able to measure the path costs to the root bridge from S2 and not from S3 because of the superiority I've talked about of S2, because of having the next lowest MAC address. And so that therefore means that from S2 going to the root bridge, it can be done in two ways. Either S2 can go to the root bridge from directly to S1, and the cost will be 19. Or S2 can go to S3, then to S1, the root bridge, and the cost is going to be 19 plus 19 here, which is 38. And therefore, our preferred path is actually going to be this part here because it has the lowest cost. It has the lowest cost. But anyway, these two are going to be our root ports. So we have elected the root bridge. We have elected the root ports here. So two ports that we have already elected so far. Only F01 on S3 and F01 on S2. We still have F02 on S1, F01 on S1, F03 on S1, F0, let's say F02 and F01 here. So let's move on. After electing the root ports, what next? Ladies and gentlemen, after you elect the root port, the next task is now to elect the designated ports. Very, very important. The next task is now to elect the designated ports. And so to elect the designated ports, guys, rule number one, all the ports attached on the root bridge will be designated ports. That's very important to note. S1 is the root bridge. That therefore means that F01, F02, and F03, all these ports around the root bridge, all of them must be designated ports. That's very important. Okay, all those ones are gonna be designated ports. Then, so we have now seen F01 tick, F01 on S1 tick, F02 on S1 tick, F03 on S1 tick. All are designated. F01 on S3 also root port tick. Now, of course, I need you to note, by the way, that any ports connected to end devices, all those will always be designated ports, because like I mentioned, all designated ports and root ports remain in forwarding state. All designated ports and root ports remain in forwarding state. Now, where is the problem now? The problem is now the link between S2 and S3. And how do we do this? Let me show you how did we get this designated port here. All right. We use the same principle. We know that S2 had a lower MAC address than S3. All right. So we start measuring the distance to the root bridge from S2, not from S3. And so we ask ourselves, from F02 here, this port here, okay, which one has the longest distance to the root bridge? Or the shortest distance for that matter? So from F02, which is connected to S2, we just need to cover the link, this link here between S2 and S1. Only this link is needed to get to S1. And the cost here, obviously, you know, is 19. The cost there is 19 because these ones are fast Ethernet ports. But from F02, okay, going to the root bridge, we will have to move to S3. From S3, that is another 19. From S3 to the root bridge. Therefore, this line is going to be the longest. That is point number one. Point number two, since S2 had a lower MAC address than S3, the end of this link here connected to S2 will have to become the designated port. And once we get the designated port, it means we are only having one port here to prevent the loop from going round and round. Only one port is remaining to break the tie, F02. And the best we can do is to block this port, ladies and gentlemen, to prevent any formation of a layer 2 loop. And therefore, this port here is going to be the root port. I mean, sorry, the alternate port. That port is going to become the alternate port. We are going to have a variety of topologies to see how that blocking comes to place. And so realize, since this port is the only port remaining, it has to be the alternate port and is the one that's going to be blocked to prevent going round and round. I have taken long to teach this. The switch just takes a few seconds and it has already blocked that port. It has already done the election of the root bridge. It has selected the root port. I mean, it has selected the designated port and it has selected the alternate port. And that's why your network begins to work immediately. All right, all right, all right, all right. That's interesting there. So at this point in time, spanning tree has finished its job. It has logically blocked one of the ports to prevent the going round, the formation of the layer 2 loop that we saw as we are beginning to learn. Let's now look at another topology. Let's look at, this is a very interesting topology here. Very interesting topology. And we want to go through it and we see what's going to happen. Huh? How can we be able to sort out this issue here? So the first thing we look at is among the 4 switches, which switch has the lowest bridge ID? All of us will agree that this is 32769.111, 32769 AAA, 32769.555, 24.5. Look at this, 24 here. So 24 is going to be our lowest bridge ID, and that's why switch S1 is a bridge ID. My only question here for someone to answer is this. Between switch S3, switch S2, and S4, S2, S3, and S4, which switch has the lowest bridge ID? I want someone to answer that. Switch S2, S3, and S4. Which switch has the lowest bridge ID?
Switch S4.
Switch S4 has the lowest bridge ID. Now, that was simple enough, and I hope everyone agrees with that because this is the 2769111, obviously. Now, which switch has the highest the highest bridge ID between S3, S2, and S4? I want to hear that.
S3.
Thank you.
S2.
S3.
S2.
Thank you. S2. Okay. Thank you. Thank you. S2 has the highest bridge ID. Why are we saying that? I'm saying that, guys, because I taught you guys about hexadecimal numbers, all right? And the hexadecimal numbers start from the first 10 decimal numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then we move to A, B, C, D, E, F, which therefore means that A is bigger than 5. Because A is bigger than 9, A is like 10. A represents 10 among the decimals. So if you look at A here, you cannot compare it with 5 here. So that's a good reminder over there. Hope you don't forget again. So let's continue and see how did they do the election here. So fast forward, switch S1 is already elected as the root bridge. And obviously, its two ports, F02 and F01, become designated ports. Those ones become designated ports. Again, obviously, the two opposite ports, the ports on S3, F01 here, and the port on S4, F03, these two ports again become root ports. So we are done with the first 4 ports. We have 4 more. Now, something is here, something that is called, I want to give you the exact word. We call it the sender's bridge ID. The sender's bridge ID. Now, the sender's bridge ID is going to happen in the following ways. We compare S3 and S4, their priority bridge IDs, and we realize that the bridge ID of S3 is 32769.555, and that of S4 is 32769.111. And that means that S4 has the lowest, bridge ID, okay? And that therefore means if S4 has the lowest bridge ID, it means that the sender's bridge ID, the sender's bridge ID of S4 to S2, all right? The sender's bridge ID for S4 is 32769.1111. Is going to be used to determine the value or the state of F01, okay? The state of F01, which is going to become a root port. So the S2 F01, F01 of S2 is going to become a what? A root port. And as usual, since this is a root port and the S4 has the lowest ID than S3, therefore, this port here of S4 is going to become the designated port. You're going to be keen enough to know that. Since this is a root port, this other end can only be a designated port, not another root port. It can only be the designated port. It's very hard to have root port. It's not easy. And the same way, it's not always easy to have designated on both ends. It's not easy. And so this is going to become our designated port, and this is going to become the root port. Now, having mentioned that, since this one here is our F01 was the root port, and since also that S2 has already, is having 2 links. S2 is having 2 links to reach the root bridge. From S2, we can go through S4 to reach the root bridge, and from S2, we can still go through S3 to reach the root bridge, okay? And so S2 is already having this other end here as the designated port, and this side of S3 is already a root port. You see, this side is already a root port. We can never have this end also a root port. A switch can never have 2 root ports by itself, okay? We cannot have F01 and F02, both of them are root ports. If this is a root port, then this end must be the designated port. And if this is the designated port, we already elected root port here. We got a designated port. We already elected root port here. We got a designated port. Then this port here must be blocked. This is gonna be our designated port. This is gonna be our designated port. And that is very, very important for us to note. That is very important for us. Okay, sorry about that. Now, having seen how the election, and this is very critical, how the election here is being done, we are now going to look at another topology. Very interesting. You will rarely miss some of this in your exams, even your own chapter exams, and even final exam. You're gonna meet them. They're gonna tell you to determine some of these things. Very interesting. All right, let's look at probably the last one. The last one is now between two switches. Remember, the layer 2 loop can always form at any of these ports. So here now we are going to use something called the lowest sender's port ID. So the lowest sender's port ID, we talked about the sender's bridge ID. Now we're going to talk about the lowest sender's port ID here. Remember, even with two, let me just look at this. Even with the two switches, a loop can still form. Okay, even with the two switches, we can still have a loop. Sorry. All right. So we are going to have here switch S1 and S4. All right. To switch S1 and S4. And these two switches are joined together or connected together by two links here. And one of the ports has to be blocked to prevent the formation of the loop. All right. Of course, we can see that S1 has a bridge ID of 24,577,333. And S4 has 32,769,111. And that is already red. There's a red alert there telling us that, S1 is going to be the root bridge because it has a lower 24. This is 32. All right. Then, of course, like I said, all ports on the root bridge must be designated ports. All ports on the root bridge must be designated ports. That's already done. We can see that. Then now, the only way to break the tie now is to make sure which of these ports, because if one end is a designated port, the other two ends should have been all of them should have been root ports, since the end of the switch connecting to the root bridge all of them are always root ports. But we are going to refuse to accept that, since we only have two switches in this case. And so in this case, we're going to use what is called the lowest sender's port ID. And that is as simple. That is not something very complicated. So to know that, you just simply need to look at S4 and look at these IDs here. This is the port ID. The first one is F06 and the second one is F05. And so the lowest sender's port ID, we are going to look at the sender's port ID from the root bridge. Okay, so you look at F01 here and you look at F02. And so the sender's port ID from the root bridge. So we have F01 sending to S4 and we have F02 sending to S4. And so the port with the lowest sender's port ID from the root bridge, which is F01, sending to F06, it means F06 is going to be the root port. Okay, because it has the lowest. The sending port ID from the root bridge is F01, so it is sending to F06. So F06 is identified with the lowest sender's port ID. So this is going to become the root port, and we're going to block the remaining one. And that is going to F05 is going to be the alternate port. Very, very interesting stuff here. Okay, and that's how we break the tie. That's how we prevent STP from, blocking. Layer 2 loops from ever forming in this particular network. Now, having said that, we want to talk about something very briefly before we can talk about the channels. Now, we do have this spanning tree has different port states, and we have already seen the port roles. Remember to differentiate between a port role and a port state. So we are now going to talk about port states. And I had already mentioned to you that the port roles were, designated root ports and the alternate ports, whereby the alternate ports is in blocking state, but the roles of designated and root ports, all of them are in forwarding states. And so when a switch is just powered on, the ports will always transition from different levels, okay? So the ports will move from blocking initially when the switch was off, it will go to listening, it will go to learning, then it will go to forwarding. You get that? Now, why am I talking to you guys about this? Because this is going to become very important. And this one, as an element of spanning tree protocol, is something that can prevent your laptop from acquiring an IP address. Listen to how dangerous that is. This is something that can prevent your desktop computer or even the printer on the network from acquiring an IP address, and therefore it's not going to be accessed over the network. That is something very serious that you need to know, because if your device is not able to receive an IP address, it has no use being on the network because it cannot be reached and therefore traffic cannot move. Okay? And therefore, blocking, listening, learning, and forwarding. The first maximum age of blocking is 20 seconds. Listening, 15 seconds for a delay. Learning, 15 seconds before it gets to forwarding. And so 20 plus 15 plus 15, that is 50 seconds. This is too much time. Can I tell you something from the industry? Every PC that is turned on or powered on needs to acquire its IP address within the first 15 seconds. Within the first 15 seconds, otherwise the DHCP process is going to expire. And if it expires, your PC will not acquire an IP address from the DHCP server. Yet, the port of the switch that is connected to your PC needs to take over 30 seconds to acquire an IP address. That is so serious. That is very serious. And so I want you to hold that knowledge there because it's going to come very important in a few. Now, STP works in an environment with only one VLAN, which is the default VLAN. But Cisco, as we will be looking at the variations of spanning tree, has what is called per VLAN spanning tree, whereby every VLAN instance, which means if you create more VLANs, every VLAN is going to have a spanning tree of its own. Okay, what do I mean? You can find one port is blocking for VLAN 2, but forwarding for VLAN 3. Look at that. One port is blocked or alternate for VLAN 10, but it is designated for VLAN 20. That's how funny it gets, and how serious. These are now the nitty-gritties of network that we need to know. And with that, we need to look at the evolution of spanning tree. Spanning tree has been evolving, all right? And the default and the first version of spanning tree was called STP. That is the original spanning tree, okay? And that was by IEEE, by the standard organization for all the vendors. Now, and this was used back in the year 1998 and earlier. Later on, Cisco enhanced STP and created its own STP called PVST plus, Pavilion Spanning Tree. Pavilion Spanning Tree. That was the one for Cisco. So it is Cisco that started now creating spanning tree instance for each VLAN because their switches were able to accommodate more VLANs than just VLAN 1. And this one came with more features, 2 of which we are going to learn today. The rest you will learn in CCNP. So there's something called port fast, was supported by PVST. There's uplink fast, there's backbone fast, there's BPDU guard, there's BPDU filter, there's root guard, and there's loop guard. Today we're gonna be talking about just port fast and BPDU guard, and we'll talk about what that means. And the word BPDU, of course, comes from the BPDU messages, Bridge Protocol Data Units. All right. Now, IEEE updated its STP version and called it the 802.1D-204. All right. Now, then IEEE developed what is called RSTP, Rapid Spanning Tree Protocol, which is an IEEE 802.W. It's from IEEE, which provided a faster convergence. And when Cisco heard of this, Cisco enhanced this RSTP to create its own what is called Rapid PVST or Rapid PVST, Rapid Pavilion Spanning Tree Protocol, which still supported BPDU guard, port fast, BPDU filter, root guard, and loop guard. All right. Then IEEE later on came up with what is called MSTP, the multiple spanning tree protocol, which is a IEEE standard, which could map multiple VLANs within the same spanning tree. But Cisco instead also came up with their own MST, multiple spanning tree, which is the enhancement over MSTP. And this one provided up to 16 instances of RSTP and combined many VLANs within the same, with the same physical and logical topologies. So there have been all these enhancements and evolutions of spanning tree that we have been having. And we just talked about the port roles and port states there. And you can see now a difference between the STP and the RSTP that were there. The STP had a kind of a disabled state, which is no longer being talked about, but we have blocking, listening, learning, and forwarding. RSTP had combined both listening, blocking, and disabled into one port state called discarding. Actually, port roles called discarding. Actually, these are port states. So there was discarding, learning, and forwarding. So those are the ones for RSTP, and these are the ones for STP. Talking about now the port states, which we have talked about already. STP had root port, the designated port, and the blocked port. The blocked port, which we are calling the non-designated port. While RSTP had still the root port, the designated port was there, the alternate port is there, but they had something here called a backup port. All these details you guys will learn in CCNP. They are not they are beyond the scope of this course, and that's why we do not cover so much of it here. Let me talk about the last thing, before we talk about ether channels. We have what is called port fast and BPDU guard. And this is where I need you to pay a little bit of attention. And I'm gonna just repeat what I said. End devices connected to a switch, when they are powered on, they normally need to acquire their IP addresses from the DHCP server within the first 15 seconds. Otherwise, the DHCP process is going to expire or time out, okay? And your device is not going to receive an IP address. And by extension, it will not access the internet. Now, spanning tree needs about 30 seconds delay to be able to move the ports from blocking, listening, learning, and forwarding, all right, which takes over 30 seconds averagely. Now, to prevent this mess, because DHCP needs 15, spanning tree needs over 30. DHCP cannot wait for spanning tree. DHCP must go fast. So what happens? We need to sort out DHCP. Sorry, we need to sort out spanning tree because it is the problem. It is the one taking more time, yet DHCP cannot happen before it is completed. So what happens? What happens? You need to configure your pods with pod fast so that the pods are going to skip some of the states, so that instead of going from blocking, listening, learning, forwarding, the pods are going to skip listening and learning, and that means they go straight from blocking to forwarding, to reduce the time it takes for DHCP to for spanning tree or STP to be able to synchronize, making it possible for DHCP to make it within the first 15 seconds. And that is something that's going to come to your exam. That's something that's going to be coming to your exam. So DHCP requires 15. So we configure the port with port fast to enable them to transition immediately from blocking to forwarding without going through listening and learning. Finally, talk about BPDU guard. Now, for the word BPDU, these ones are the messages that are used in the election process within spanning tree to elect the port states or port roles, including the root bridge. Now, BPDU messages should only be received on ports joining switches to switches, okay? Because that's where the election takes place. A BPDU message should never be received on ports connected to end devices, because those ones are the access ports connecting to the end devices. And so, what if a port connecting to your laptop or your desktop computer receives a BPDU message, and it is the one that is selected to become the alternate port? What's going to happen? If the port connecting to your laptop or desktop computer is elected as the alternate port, it means that port is going to remain blocked and you're not going to access the internet. So what happens? We need to configure this port with what is called BPDU guard feature, BPDU guard, so that those ports should never receive any BPDU messages. But if they do receive the BPDU messages, the ports should be protected so that these ports are going to go into an error disabled state, okay, upon receiving any of those BPDU messages. And this is going to protect the port from any loops that might happen, because the port is going to shut down, okay? And you must go to the port and say, shut down, no shutdown, to be able to remove it from an error disabled state. And that is the work of what is called BPDU guard. So you've heard of those two, port fast, BPDU guard, all of them configured on access ports connecting a switch to an end device, So that is the end of this part of the class. And at this point in time, I wanted us to talk about a very small concept called